We present memory anchors for continual robot learning. In a real-world deployment, a robot may need to learn multiple tasks in sequence, like these series of jars to open. These jars look similar, but require different opening strategies. When you train a robot to open the first jar, it learns properly. When you train the robot to open the second jar, it also learns properly. But on this policy, if you ask it to open the first jar again, it uses the second strategy on the first jar. This is an example of catastrophic forgetting, where learning a new task destroys old task knowledge. A common way people have been dealing with catastrophic forgetting is a technique called experience replay, or ER. ER keeps a buffer of past task data during new task training to encourage the new task and the old task to coexist in the policy. In our work, we claim that in this buffer, a small set of memories is doing most of the work. We call these memory anchors. We hypothesize that catastrophic forgetting happens when new task data shares overlapping observation representations but requires different actions. Old task data that serves as counterexamples to this conflicting new task region helps the most. These are our memory anchors. We devise a three-step method defining memory anchors. First, we find new data that is most similar in representation space to this old data. Second, within this selection, we find the new data that has the most action disagreement, which is the difference between what the new action labels are and what the existing policies think they should be. Third, we use the same observation representation space to select old data most similar to this conflicting new data. These are our memory anchor candidates. For more information and motivation, refer to papers section 3 and 4. To test these memory anchors, we run a continual learning test on the Libro benchmark using ER with a randomly selected buffer. The graph represents how much the policy is forgetting. Higher is more forgetting. Then we run it again, but this time we prevent ER from sampling 1%, 5%, and 10% of the best memory anchors. Consistently, the fewer memory anchors available, the worse the forgetting. If removing memory anchors makes forgetting worse, can adding memory anchors reduce forgetting? In our next experiment, we add more memory anchors by setting aside 10% and 20% of the buffer to the points extracted by our method. We call this approach anchor ER. On the most conflicting task pairs, adding more memory anchors reduced forgetting. But do these benefits expand beyond a simulated task suite? In our final experiment, we look at the 3 jar tasks we showed previously. We train the jar behaviors in sequence. Using our method, the detected action disagreements reasonably select the region around the jar conflict, and the resulting memory anchors also focus on the jar interactions. A randomly selected ER buffer struggles to maintain the first 2 task behaviors when it learns the third lifting behavior, while anchor ER can preserve these behaviors fine. Interestingly, a randomly selected ER buffer also struggles to allow the policy to learn a second behavior after learning the first, an example of plasticity loss. This problem does not happen with anchor ER. The quantitative results are shown here. In conclusion, catastrophic forgetting is caused by new task data that is similar in observation representation but different in required action. Old data similar to this conflicting new data will help anchor past performance, which we call memory anchors. By finding these memory anchors, we can make conflicting tasks easier to learn in sequence. For more details and other experiments not discussed here, please refer to our paper. Thank you.